Alright, so today I'm going to explain the four fundamental forces. Now we're going to start with gravity. Now, traditionally, gravity is considered an attractive force between two objects with mass. In fact, there's an equation to represent this. It is the force between those two objects is equal to the gravitational constant times the mass of the first object times the mass of the second object over the distance between those two objects squared. Now, in case you're curious, the gravitational constant is equal to 6.67 times 10 to the negative 11th meters cubed per kilogram second squared. So, when you plug in the mass of one object, the mass of a second object, and the distance between those two objects, you will get an accurate value of the force between those two objects. Now, this is traditionally how gravity was interpreted. However, more recently, we have realized that this isn't entirely accurate. Instead, gravity is a bending of space-time caused by objects with energy and momentum. Now, to give you an idea of what the bending of space-time is, imagine that your bed is the space-time continuum. Now, set an object on your bed. You'll notice that your bed kind of curves towards that object. This is equivalent to the bending of space-time. Now, if you set another object on your bed, of course assuming you set it close enough due to friction, but I'm not going to get into that now, those two objects will roll towards each other. If one object is significantly bigger than the other object, you won't notice the bigger object rolling, but both objects do roll towards each other. Now, this can be interpreted as an attractive force between the two objects, but in actuality, it is more the two objects following the natural curve of space-time. Now, the reason we know that gravity is caused by objects with energy and momentum instead of objects just with mass is due to light. Now, before I get into this, all objects with mass also have energy and momentum. So, that's kind of a necessity. Now, the reason we know it's energy and momentum specifically, though, is because light is observed to be under the effects of gravity. We have seen light bend around planets and other large objects with a lot of energy and momentum. Now, light has no mass. It does, however, have energy and momentum. So, from this, we determined that that gravity must be caused by energy and momentum because light is affected by it and it has no mass. Now, gravity itself is theorized to be caused by particles called gravitons. Now, gravitons, as of yet, have not been detected, and this is because they are quite difficult to detect. They are considered to be both massless and chargeless. Now, they're chargeless because some objects are not affected by electromagnetic forces, so if gravitons were charged, then they would be affected by electromagnetic charges, which means all objects would be affected by electromagnetic charges. And since they're not, gravitons are chargeless. Now, they're considered massless because the distance a force-carrying particle, called a boson, the range it has is determined by its mass. Now, since gravity has an infinite range, the boson must be massless. So that's why gravitons are considered massless, because gravity has an infinite range. So, gravitons are difficult to detect, but if we do find them, we will know that our model is correct, and they are in fact what cause gravity. Next we have the electromagnetic force. Now, the electromagnetic force is a combination electric and magnetic force that occurs between charged particles. Now, there are two types of charged particles, positive and negative. Now, likewise, there are two forms of electromagnetic force. It can either be attractive or repulsive. If it is between two like particles, i.e. positive-positive or negative-negative, it is a repulsive force. However, if it is between two opposite charges, i.e. positive-negative, it is an attractive force. Now, like the gravitational force, there is an equation to model the electromagnetic force. And it is the force, either attractive or repulsive, is equal to 1 over 4 pi times the charge of the first particle times the charge of the second particle over the distance between them squared. And that is then times 1 over the vacuum permittivity constant plus the vacuum permeability constant times the velocity of the first particle times the velocity of the second particle. Now, notice the similarities in this first section to the gravitational equation. We have a constant, we have our Q1 and Q2, which are equivalent to the masses of the two objects, and we're dividing it by the distance between them squared. So there's a definite parallel between the force equations. Now, I should also point out that just because our understanding of gravity has been updated, the equation for our gravitational force is still valid, even though our understanding has changed. It's still a very good approximation of gravity. Now, over here is where it gets a bit different. We have 1 over the vacuum permittivity constant, which is for the electric force. And just in case you're curious, EO is equal to 8.85 times 10 to the negative 12th coulomb squared times second squared per kilograms times meter cubed. So this section is for the electric force. Now this other section is then for the magnetic force. And the vacuum permeability constant, notice the distinction there, permittivity versus permeability, but this is equal to 4 pi times 10 to the negative 7th meters times kilogram per coulomb squared. Now, this is then times the velocities of the two particles. So, if either of the particles is not moving relative to your reference frame, there is no magnetic force. It is all electric force. But the electric force is always in existence. You always have an electric force between charged particles, but you only have a magnetic force if the two particles are moving relative to your reference frame. Now, the electromagnetic force is caused by photons. Now, like gravitons, photons have no mass, which means that the electromagnetic force goes to an infinite distance, as it has been observed to. However, unlike gravitons, photons have a charge, which is expected if it's the force-carrying particle for the force that relies on charge. And again, unlike gravitons, we have detected photons because they have a charge. I mean, photons are light after all. Now we have the weak nuclear force, more commonly called the weak force. Now, the weak force causes both fission and fusion. It causes particles to both decay and to fuse together. Now, there are two particles for the weak force. There is the Z boson, which is a particle with mass, but it has no charge. And then there is the W boson, which has mass and a charge, either positive or negative. Now, when both of these interact with an atom, we'll draw a proton here, they cause particles inside the protons, called quarks, to change, which can turn a proton into a neutron and cause the atom to start splitting apart. So that's an example of nuclear decay. So these particles are very useful in the process that powers our sun and that works to provide nuclear power. And lastly, we have the strong nuclear force, more commonly called the strong force. Now, the reason it is considered the strong force is because it holds atoms together. So, if we look at a proton, inside it, as I mentioned earlier, it has quarks. 1 down quark and 2 up quarks. Now, the force-carrying particle, or boson, as I mentioned at the beginning of the video, for the strong nuclear force is the gluon. Now, the gluon is what holds these quarks together. So it'll hold the down, up, and up quark together within a proton. so it allows a proton to exist. And it does the same thing for neutrons, except in neutrons, there are 2 down quarks and 1 up quark. So it holds it all together. Now, as I mentioned, for the weak force, what it'll do is it'll change one of these up quarks to a down quark, turning this from a positively charged proton to a neutrally charged neutron, which will cause then the atom to start splitting apart. Now, electrons are not caused or are not governed by the gluons, because electrons are actually elementary particles themselves. As far as we know, there is nothing inside an electron. Now, the strong force is in fact so strong that it has a residual effect in the atom. It'll actually hold protons and neutrons together and protons together. So it is what actually keeps the atom in its shape. It allows the atom to stay together. Now, gluons have mass, and since they have mass, they have a finite range. So the strong force has a limited range to which it will affect. But it is still a very strong force, and it's what allows us to stay together. But yeah, so those are the 4 fundamental forces: gravity, electromagnetic, weak, and strong, all caused by force-carrying bosons. So, I hope you learned something, and see ya!